Okay, this is going to work with Wei Shu, who's at Yahoo Research right now, and Zubin Garamani. So let's switch gears for a moment here, and instead of looking at clustering problems, let's look at prediction problems like classification and regression. So you want to predict y given x. And the standard setup for that is you have a sample of size n of x and y's. You infer some theta, which can be a point estimate or can be a posterior distribution, and then use that to infer a new value for, an xy, your next y. But there are some problems where even conditional on theta, your model parameters, your data points y's are still dependent. And you can imagine these types of process emerging from relational data. This is data where you have links between data points. And it's easy to explain that through some examples. For instance, you have a problem of classifying web pages in different categories. Like this web page is a news article about sports, this web page is a news article about politics, and so on and so forth. And you also have some link structure that is given by the own structure of the World Wide Web. And this link structure tells you some other information about how these web pages are dependent on each other. And you can create other relationships from data. For instance, you can look at which movies are rented often together in a rental movie website to tell you a new type of relationship between movies. And the issue is how to use this data, this type of link matrix, with your feature data in your standard regression classification problems. So just to make an analogy with other things you might be familiar with, if you're familiar with time series processes, there's some type of relational problem too, where relation here is time. It depends between continuity along a timeline. And usually in these problems you have some type of independency structure. You might, for example, assume that 2 points are independent given an intermediate point. So again, in our work here, again, use this idea of assuming there is some Markov structure there in your domain that you're going to use to define how these relationships are propagated. So how can you use this link information? So let's assume for now that two moves are rented together because they have many common factors shared. They have many common features. And these features affect the ratings that those movies receive. So you have this problem of predicting ratings of movies. And you have something like this. You have movie features, you have ratings, and you have all these hidden common causes between these labels. But here, not really interested, unlike in Zubin's talk, on discovering which features are there. You're just going to use this idea that the relationships that you observe in your data are surrogates for possible hidden common causes between the labels you want to predict. So the idea is, given this link structure, which is part of your data, you postulate some hidden common cause structure based on it, and you're going to define a set of independence constraints based on these relationships, and an algorithm that is able to give you posterior quantities on your predictions. So to give you an example, this is a problem of classifying books. You basically have, you want to classify a book as being a political book of liberal inclination or conservative inclination. And your features here are taken from things like the description of the book, the very text that describes the book. And you have here a network of which books are bought together often by the same customers. And you have, for example, this graph, which is nearly invisible, depicting a link matrix of 105 books, where each red dot that you see there is a pair of books that are bought often together in Amazon.com. So basically I use the Amazon.com front page for each book as features for them. So the word distribution there are my features. And the problem here is just a binary classification using the label data for that. So the thing is how to solve a problem like that using both the features that are collected and this link matrix that is also given to me. So we start by showing some relationship of this problem with some classical problem in econometrics. And I'm going to build a relational model inspired by that classical model, and I'm going to generalize it in several different ways that I'm going to explain. And also what's the algorithm problem of trying to do inference with this model. So this is a model from the 1960s known as similar and related regression. You have to predict, let's say, the features of two objects, 1 and 2, the labels of two objects, 1 and 2, again, features of these two objects. And one characteristic of this problem is it's basically a capital regression problem. You want to predict y1 with features from x1 and y2 from features on x2. So for example, if you regress y1 on x1 and x2, x2 would not have a significant coefficient, it would just drop over the equation. It's not a predictive piece of information for your label y1. What was interesting about this couple problem is if you regress y1 on also y2, your old feature x2 is now has a significant effect on y1. So what's going on there? So this is a type of problem where we have these two objects, General Electric and Westinghouse here, the two companies, for instance. And there are several hidden common factors affecting stock prices here simultaneously. And once you regress one element here on everybody else, it creates a dependency between these two elements. So I'm going to use the same idea here, where just for simplicity, since we're not interested in which hidden common causes are there, I'm just going to represent that existence of hidden common causes of bidirected edge. This is known as a mixed graph representation. And when you have a relational problem, you're going to have several objects here. You have 5 objects. And the link matrix is going to be interpreted as an indicator that there is some hidden common cause between these vertices. And that defines a model, a dependence model. So if you have this structure of dependencies, what exactly is the model behind them? So what we're going to use here is a non-parametric probability regression model for y given x. So there is some hidden function, there's some hidden function f of x, and I'm just going to add some Gaussian noise to it, and the link function for my binary problem classification here is going to be the probability link function. In our particular case, I'm just going to use a Gaussian process prior for this hidden function f of x. So the catch here is how to use these error terms to express relational dependencies. This is just yi given xi. What does it mean to relate to the different yi's? We are going to make the error terms of this probability regression problem to be dependent instead of independent. And just so it's going to be clear later, you are going to re-represent this error term as a sum of 2 different terms, epsilon star and zeta, as follows. You are going to make this epsilon star a set of independent Gaussian variables. In this zeta error term here, a set of dependent error terms, dependent according to relationships. So if you originally have your error terms having a covariance matrix sigma epsilon, now we are going to re-represent that as some sigma epsilon star and some sigma zeta, where this matrix is not diagonal anymore. This matrix has non-zeros on places where you have 2 pairs that are related. So if you're this is actually convenient if I use a Gaussian process prior, because you can re-express your original parameterization here of f plus epsilon by separating epsilon and zetas and epsilon stars. Now grouping these 2 elements together, you get a different function g of x, which can also be represented in the same way a Gaussian process can be represented. If you're familiar with Gaussian processes, you know to define the phi, you only need a covariance function represented as a kernel matrix. So since these two are independent, you just get a different covariance function with, sorry, this should be zeta here, with a different kernel. So you can basically use everything you have for Gaussian process classification into this framework. But the issue here is difficulty on defining what sigma of zeta is going to be. Just as a parenthesis, to actually do the computation of this model to calculate posterior distributions over your g of x to make predictions, we are going to do that with some algorithm known as expectation propagation, which some of you might be familiar with here. So we're going to approximate the original posterior, which is a truncated Gaussian, which is hard to integrate in high dimensions, with a Gaussian posterior distribution. And it's actually going to be clear here why you made that split of the error term into epsilon star and a zeta. Because in expectation propagation, what we do in a very high level sense is to take each of these factors one at a time and approximate that with a Gaussian according to some measure of distance between distributions that you minimize. So if you're going to approximate this with a Gaussian, if you didn't have that epsilon star term, this will be a deterministic function, be a really bad way of approximating it. So just separate these error terms so this becomes a more sensible approximation for that particular factor. Okay? And you can generalize this framework for the types of problems. If you have more than one relationship, you can have, for instance, movies that are rented often together and movies that get shortlisted for particular prizes together and so on and so forth. There's different types of relationships, and you can apply the same idea of decoupling the error term as sums of different error terms and have different covariance functions over each one of these elements. Now, the catch is how to parameterize this covariance function of the error terms, and this is not an easy problem. Because we want it to be positive, definite, and have zeros in the right places. And we want it to be also easy to estimate, because you know the number of elements in this covariance matrix is going to increase with the number of data points. And to define a matrix with zeros constraints is not that easy either. If you look at a problem where you have 3 elements and the absence of an edge here means basically these 2 elements aren't correlated, you can't just start with a positive definite matrix and poke zeros on it, because it is not guaranteed to give you a positive definite matrix. Instead, I'm going to use an indirect way of parameterizing that. So suppose now we can find all cliques in this subgraph defined by the labels and the bidirected edges. Suppose you can find all cliques on that graph. We are going to create some type of factor analysis model where for each clique introduce a latent variable. For each member of the clique is going to be a child of this latent variable in a graphical modeling sense. These latent variables are normal 0-1 variables, and the coefficients in this model are equal to 1, like in this example here. So suppose you have these 4 variables, okay, and you're going to find one clique. You're going to find the cliques for this graph, create a latent variable model of latents like this, and parameterize this model with each variable being a sum of its parents with some error term. This is a very nice intuitive interpretation, because the covariance between 2 terms is proportional to the number of cliques they belong together. It's inversely proportional to the number of cliques they belong to individually. You can just calculate the implied covariance matrix. It's just going to be a count of memberships in cliques. So a very simple parameterization. And you're going to introduce a single hyperparameter for that. We are going to define this correlation matrix that is a result of this model, and you're going to weight that by some hyperparameter rho. So when rho is 0, the covariance matrix the final covariance matrix here is going to be the diagonal matrix. And when rho gets larger, the contribution of the relationships increase proportional to the number of cliques they belong together. Okay?
Sorry, should that be, that bracket, should it be 1 minus rho multiplied by u diagonal?
Oh, no, the identity minus that.
Okay. So when rho is 0, then it becomes the identity matrix.
Yeah. Because it's a classification problem, you don't need to worry about the scale of the actual error term. Okay, there are some problems with that. You can find out cliques. It's a computationally hard problem. So you introduce a simple approximation where you triangulate the graph and then you extract the cliques out of that. It's a type of relaxation because now you're throwing away some constraints. You have some independence constraints that disappear when you introduce an edge by triangulating the graph. So we can see that as relaxation of the problem. Sometimes they might have not very nice side effect. If you have this original matrix that I showed to you, or the political books, if you triangulate it and create your final correlation matrix, error terms is going to look like this, where you have many more spurious relationships you didn't have before. Although the strength of these relationships you can see are still related, you can have this component here and this component there, still related to what the original link matrix was. But still, this doesn't satisfy the original problem where you wanted to have zero correlations between independent, non-related data points. And there are different ways you can parameterize this matrix. I just showed one possible way. There are simple ways where you can introduce an independent hidden variable for each edge and again define a latent variable model, but this has disadvantages of its own. Can I just show if you do this, your correlations will tend to 0 when you have many, many elements in your variable, in your graph. Although this is much easier to compute because you don't have to find cliques. Okay? So if you have a matrix like this and you introduce that particular parameterization, you're going to have a very weak set of correlations between your data points. As a consequence of that particular way you derived your covariance matrix. But here you don't have spurious relationships anymore. So there is some disadvantages and some advantage on doing that. So there is a comparison. You can imagine also other models for relational problems, which I'm not going to go into details here. But instead of having these bidirected edges that I mentioned, we have these undirected edges. That means a different type of dependency model. So with models where you have undirected edges, if you have observed data points in your data, these data points are going to block dependencies between the unobserved data points. So this pair, for example, is blocked in an undirected network if you observe this in your sample. While the bidirected network is a complement of that. If you observe this label, for example, this observation is going to create a dependence between them, between these two test points. So we have these two choices of which relational model you have. There's some motivation for that undirected model too, which I'm not going to cover. But the idea is if you think your link matrix is a surrogate for some hidden common causes, then it makes more sense to use a model like this. So what I'm going to do is just to make a short comparison between the model I just described with a Gaussian process and that particular choices of correlation matrices for the error terms, and some other model that is based on this idea of undirected networks. It's also a Gaussian process model, but the way the relationships are defined is with this particular independency structure of undirected network. So the first experiment, all three examples are in text classification. So this first experiment is on classifying papers of being from some particular topic. And here I'm going to focus on binary classification. So you have over 4,000 machine learning papers, but I'm going to focus on two classes here, two classes at a time. You don't need to understand what class that is. It's just one class 5 against some non-class 5 papers. The criterion you're going to use to tell which algorithm is better is the area under the curve. If you are not familiar with area under the curve, you can think that as a ranking criteria. If you rank true positives as being more probable than false positives, then you get a high AUC. If your rank of true positives and false positives doesn't have a good separation, then you have a lower AUC. So the higher the better, and this is from 0 to 1. Okay. So in the first experiment, we are going to use this database of papers. Features, again, are just words in the papers, treated as a bag of words. And we are going to use, we actually have 4 different methods. We have a standard Gaussian process without the relational information, the standard Gaussian process where the actual adjacency matrix is just transformed in a binary vector and giving us extra features for your problem. And we have this other relational Gaussian process that uses an undirected network representation, and we have our own model, which we call mixed graph GP, which is just XGP. This problem is actually quite easy, this classification of papers. So you're going to use only one, just for illustration purpose, you're going to use a very limited part of the data as observed data. You're going to predict the other 99% papers using this observed part of it. So you can see that in terms of area under the curve, our method easily beats the standard Gaussian process with relational information. And even when you add the adjacency matrix as input features, you still don't get much of an improvement in the Gaussian process. But our relational model gets a reasonable improvement over in terms of predictions in AUC. But unfortunately, the other model that uses undirected network here works much better. Well, not much better, but it gets easily to the very high AUC. This is a model, a problem where you use very, very little training data, very, very little observed data points. So you don't expect our model to propagate this information for many unobserved points because you have very few observations in the data. But things get more interesting when you add more data. In this political books problem, for instance, we are using higher sample sizes of observed data for making predictions, and you're getting an AUC of 0.98. It's also very good. These are easy problems in some sense. You get very good separation between positive and negative elements. So you get 0.98, and also the other model where the undirected network gets about the same thing. But the most interesting case is this harder problem of classifying web pages on different topics. So for example, we have student pages and faculty pages and project pages and so on. You have one particular binary classification here. In this case, this problem is not as easy. You don't get as high AUC numbers as you get on the previous problems. And for example, when you use Gaussian process classification, you have this type of AUC results for 4 different universities. You have 4 different data sets for 4 different universities. Using our relational Gaussian process, you get the best results out of these 3 with some very significant difference between this undirected model and our model based on hidden common cause relationships. Okay. So that's basically it. I showed a very, very simple model. There is only one hyperparameter. You can imagine models where you have, for example, hierarchies of parameters for your covariance matrix. Since you always have to deal with this problem where your number of entries in the covariance matrix increases with the number of data points. So you can't just attach a different parameter for each entry in the covariance matrix unless you restricted them somehow. You can also think in terms of using generalize that for the case of heteroscedastic noise, where a covariance matrix of error terms depends also on your input. So for different inputs, you have different variances. And this thing I mentioned briefly before, a mixture of relationships, you have more than one relationship, so use different types of covariance matrix for different error terms. Maybe some different approximation algorithms besides the expectation propagation using. And other types of problems you can imagine that are related to prediction using relational classification. Okay. So that's it. I would also like to mention that there is some source code for that on my webpage, some MATLAB code. So if you want to play with it, you can just go to my homepage. It's for MATLAB, and use it immediately. Okay. Yeah.
The usual way to get these output covariance matrices is simply to use latent Gaussian process factors, and then they just drop out as a byproduct. Like you have, for example, a factor model, you sum Gaussian processes and then bring your correlation. Can you do that here as well? I mean, it seems like you're just approaching the thing like, oh, how can I find a good covariance function? But
Well,
I mean, why not saying how can I find a good latent model?
yeah, but here I'm using some data too, right? So you have this data that is a link matrix. The thing is, how are you using this data? If I just introduce extra latency and ignoring the link matrix, you're just throwing away data. So what do you do with it? It's not just a measure.
It's a bit like a model. I mean, it's kind of a model learning problem, right? I mean, you could suppose that there are some latent factors which are combined in a parameterized way. You have to learn that parameters as well, and so on and so on. But is that too big then?
Well, this is a model with latent factors parameterized in different ways, right? You still have some latent factors. You're just seeing in which ways you can use those latent factors, because it's not determined from the structure of the link matrix, right? If you have clicks like this, it's not clear which is a latent structure that generates that. If it's just one latent variable per click, it's several latent variables per click. You see what I mean? There are different ways where just by observing this link matrix, that it's not very clear which latent factor latent factor model you want to use. And there's a way of thinking which different parameterizations you can have for that. Okay.
So if you have multiple different kinds of relations, you could actually put a parameter in front of each of those matrices and then learn which kind of relation is important for predicting.
Right. This is actually known as mutual kernel learning, right? This is a type of mutual kernel learning for a fixed training test problem. So you learn a convex combination of the kernels of these error terms.